Welcome everyone. Today, we'll explore why the reference clock in high-speed SerDes links effectively establish the minimum jitter level you can achieve. A concept often called the jitter floor will cover how jitter budget tighten at high speed, how the transmitter, receiver, PLL and CDR loop filter jitter, and why reference clock quality become a critical performance-defining component at multi-gigabit rates. In high-speed SerDes links, jitter budgets are extremely tight, often on the order of hundreds of femtosecond RMS. Modern wireline protocols like PCIe and Ethernet require sub-picosecond jitter at speed of 10 to 25 gigabit per second. Even if the SerDes circuit were perfect, any phase noise on the reference clock will propagate through the link and could be amplified by the PLL. Thus, the quality of the reference clock strongly influences the final signal integrity. If the reference clock jitter is not properly managed, it can dominate the total jitter budget and degrade link reliability and PLL rate. One design rule of thumb is that the reference clock jitter should stay well below the total jitter budget. Otherwise, the reference clock noise itself becomes the jitter floor, limiting how clean the data I can be. In this presentation, we'll quantify how reference clock noise appears at the transmitter output and explore system-level choices to minimize its impact for reliable link performance and target PLL rate. On the transmitter side, a low-frequency reference clock, for example, 156.25 MHz, fits a clock multiplier unit (CMU) containing a phase lock loop (PLL). The PLL generates the high-speed series clock needed for the serializer, typically driving a CML output driver by multiplying up to the reference clock. On the receiver side, the incoming series data goes into a clock and data recovery CDR circuit, which extracts a clock from the data transitions. The CDR uses its own PLL to recover a sampling clock that aligns with the incoming data bitstream. The key point is that any jitter on the reference clock enters the transmitter's timing loop via the PLL. The PLL attempts to track this phase noise, effectively transferring and often amplifying it onto a high-speed signal data stream. The noise then propagates through the link, establishing the fundamental jitter floor. In other words, the transmitter cannot output a signal cleaner than its reference clock within the PLL bandwidth. Ethernet and PCIe requires reference clocks with very high frequency accuracy, typically within plus minus 100 to 300 parts per million ppm. More importantly, the allowable timing jitter in this protocol is extremely small and shrinks at higher speed. For example, PCIe Gen 3, 8 gigabit per second, permits roughly 1 picosecond RMS jitter, while PCIe Gen 4, 16 gigabit per second, allows about 0.5 picosecond. The 25G base KR 25.78 gigabit per second Ethernet standard permits only about 0.57% over the unit interval, roughly 220 femtoseconds, as random jitter. This number represents the total jitter ceiling for the transmitter output at each data rate. In practice, the reference clock jitter must be only a small fraction of the budget. If a low-cost oscillator already consumes much of the budget, the link may fail compliance before any other noise sources are accounted for. This shows that ensuring a high-quality reference clock is critical for meeting these stringent link specifications. The transmitter's PL acts as a low-pass filter for reference clock noise. Inside its loop bandwidth, the PL actively tracks the reference clock, so low-frequency phase variation on the reference are passed through to the output. Moreover, because the PL is multiplying the clock up to a higher frequency, this in-band noise is amplified by 20 log n, where n is the frequency multiplication factor. For example, going from 156 MHz to 12 GHz, n equals 77, amplifies phase noise by over 40 dB, turning a tiny oscillator jitter into a significant output jitter. Outside the loop bandwidth, the behavior is reversed. The PL attenuates reference jitter at high frequencies. Conversely, high-frequency noise from the PL's VCO is suppressed at low frequencies. The key takeaway is that within its loop bandwidth, the PL cannot improve on the reference clock. It transfers and multiplies the reference noise directly. This is why the reference clock effectively sets the jitter flow. The transmitter output cannot be cleaner than the reference within the PL bandwidth. The receiver's CDR loop also filters jitter, but with a different purpose. The CDR is designed to track the incoming data, so it follows low-frequency variations and wanders in the signal. In effect, the CDR loop behaves like a high-pass filter for a jitter. It cancels out or tracks out its slow jitter components that are within its loop bandwidth, while passing the faster jitter components. Any jitter at frequency above the CDR loop bandwidth cannot be tracked, and therefore appears as timing error at the sampling point, degrading the bit error rate. This is exactly why standard like Ethernet defines the CDR bandwidth as the cutoff for compliance measurements. For example, around 4 MHz for 10G base KR and 10 MHz for 25G base KR. In practice, we measure transmitter jitter using an equivalent high-pass filter at the CDR bandwidth to model the worst-case receiver behavior. We conducted a test on a 25.78 gigabit per second SerDes transmitter using 3 different 156.25 MHz reference clock sources. The 25G base KR specification requires that transmitter's random jitter be below about 0.57% UI, roughly 220 femtoseconds. With a standard library oscillator, the major output jitter was around 0.72% UI, roughly 279 femtoseconds, which fails the specification. Replacing it with a mid-grade oscillator, for example, SiTime 9120 MEMS, reduce the jitter to 0.5% UI, which meets the limits. A high-end oscillator, for example, SiTime 9346, yields 0.42% UI, providing additional margin. This case study illustrated at 25 gigabit per second, the reference clock choice can make or break the compliance. The lab's clock noise alone overshoot the budget, while better clock brought the link into spec. In practice, the reference clock quality directly determines link performance. A noisy clock can consume entire jitter budget, whereas a clean clock keeps the system safe. We repeated a similar test on a 8 gigabit per second link for PCIe Gen 3 using the same reference clock. The jitter specification here is much higher, about 1% UI RMS. For example, 1250 femtosecond. With the left clock, we measure 0.78% UI of the jitter, and with the higher-end clock, 0.74% UI. Both results are well under the budget. The difference between the worst and the best clock was only about 45 femtoseconds in absolute terms, which is negligible compared to the total budget. At this low data rate, other system noise sources dominate the jitter. In other words, the reference clock noise is essentially in the noise flow at 8 gigabit per second, unlike the 25 gigabit per second case. This shows that while the reference card quality always matters, it becomes critically important only at higher speed. Several factors combine to make the high data rate extremely sensitive to reference card noise. First, the unit interval bit pair shrinks as the rate increases. So, a given amount of absolute jitter components to a larger fraction of the bit time. Second, standards demand tighter relative jitter budget at higher rates. Third, a higher series rate requires a larger PL multiplication factor N, which amplifies reference card phase noise by 20 log N. This triple whammy means that at multi-gigabit speed, even small reference jitter can quickly consume the budget. One way to counteract this is to use a high reference clock frequency, FREF. A higher FREF means a smaller PL multiplication factor is needed to reach the same series rate. A smaller N reduces the noise gain, effectively lowering the jitter flow. Thus, designing with a faster reference clock is a powerful tool for preserving the margin. Clock choice can affect flexibility and noise. In-band phase noise performance is similar where using a simple crystal oscillator, XO, or an XO plus a PL chain, since the SerDes PL dominates the in-band noise. However, an XO plus PL chain can offer benefits. It can generate multiple frequencies over a higher FREF for different protocols and provides flexible clocking across lanes. Where possible, use a common reference clock for multiple SerDes channels. A common clock architecture shares any low-frequency drift across the lanes, allowing the receiver to track out collectively and improving tolerance. For distributing the clock, use high-quality differential signaling. For example, CML or LVDS with proper termination. Now the clock as matched impedance control pairs, shielded by solid ground parent. If the clock is distributed on chip, ensure the RC time constant of the pad is much less than the clock period. For instance, RC less than 0.1 T, so that the edge remains sharp. Here are the summarized images showing you why reference clock sets SerDes jitter flow. So always budget for reference clock jitter as a first-class element in your SerDes design. Use realistic analysis filter that reflect the actual PL and CDR bandwidth. For example, standard masks like 4-16A rather than the old 12 kHz to 20 MHz big wall filter, which can mislead components choice. Specify a reference card whose phase noise is significantly better than your total jitter budget requires, especially at 25 gigabit per second and above, if the budget is tight. Raising the reference card frequency can provide additional margin by reducing the peel modification factor. Finally, remember that even a clean oscillator can be degraded by a noisy system. Ensure a clean power delivery network and careful layout to minimize power supply induced jitter. By approaching the design holistically using common clock architectures, careful clock distribution, and robust power integrity, you can avoid having your link limited by unnecessary higher jitter flow. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and place your comments down below. Lastly, please share the video with the people who may be benefiting from it.